Okay, I wanted to make a couple of videos, brief videos, one or two of them only, going over what will essentially be a crash course in linear algebra. A lot of linear algebra concepts came up today, and I think for the most part, we're comfortable with what was going on, but some of the finer, more conceptual things are a little more nebulous, and I think that we would all benefit from devoting a little more time to them, just so that certain things are more clear, such as the whys. Why do we do certain things? Why do we do them the way that we do them? All of that sort of stuff I want to make a little more clear. So I'll do two videos. This first one will be the intuition of what we're doing and why we're doing it. And the second one will be actually puzzling out an example, actually doing a calculation and figuring out how all of this is actually implemented. So with that, I'll begin with this intuition video. And for that, we must remind ourselves what an eigenvector and an eigenvalue is. So for that, we will take this graph here, and we'll look at it and we'll say, maybe we want to draw a vector on this. So consider this vector that we've just drawn, which we'll denote as v. We can see that it is 3 long and 1 tall, or in other words, it's 3 on the x-axis and 1 on the y-axis, where we have x and y here. We could, if we wanted to, define some linear mapping, some also called a linear transformation, A, in which we would shift our space around in such a way that a certain qualities of the space we're in are preserved, but we're allowed to move certain other things around. So we might want to define A such that our space, which we'll denote by a capital X, maps to, and perhaps we'll denote our new space as W. So we have this linear transformation, this mapping, X maps to W under the influence of A. What might that look like? Well, if we go down here, we can see this might be such an example of some spatial deformation of X under A. And what we have is that vector that we defined earlier. Well, because the space in which that vector lives has been stretched, it's been moved about, it's been transformed from X to W. When we are considering this vector V, we must consider the effect of A on V, just like on all the other vectors in this space. And so we might say, well, this is the point that used to be 3. Everything has stretched a little bit, so it might be a little longer. It might be nearly 4 now. And we'll say 4, 1 there. Now, we'll note something, which is that if we compare these two spaces and the associated V vector there, sure, under A, V has been stretched. V is a bit longer in the X direction. But whereas some vector that went maybe up like this, well, now everything has been shifted. It's an entirely new vector. right? It has a new angle, a new height, and a new length. V remains mostly the same. Other than this scalar multiplication, we have V lying on the same line that it previously was on. So it is mostly invariant with respect to A. We can denote this as, let's say, A times V actually equals some lambda, some scaling factor, times our original V. And that's the only change that this linear transformation has induced. In this case, V is an eigenvector of A. It is a vector such that under A, V remains mostly the same. It's just scaled by some value lambda, and lambda is our eigenvalue here. That is what is scaling V. Okay. So if we get rid of all of this, we can table that for just a moment. And we can go back to now the differential equations, defining some dynamical system. If we say, perhaps we want to define this as x dot, again, that's the temporal derivative of x, so dx dt equals x, and y dot equals y. We can define the current state of this system as some value for x and some value for y. Everything in this system, even though it's evolving through time, it's given by some current x and y's. And anytime we have some sort of dimensionality like that, we can depict this in some sort of dimensional space. So what we might want to say now is, now in the tutorial, I believe they used the components of the state vector x, and you had x1 and x2, right? I've used x and y because I think it's a little easier. So we have y, we have x, and we can say we have a whole bunch of initial states, right? Ones that populate this space, which give us an initial x and an initial y. And so we can define this whole thing by this set of coordinates x comma y. Now, that's a really good sort of preliminary result, but it doesn't tell us a whole lot about the actual system, right? Because we're looking for the temporal evolution of these equations, and we're looking for the state through time. So one thing we can do is maybe get rid of that and say, what if we had x comma y comma t, right? If we had some three-dimensional space, we would add third dimension onto this, and we would look at the behavior of all of these points through time. Let's say it was something that we knew had some exponential decay. For every single point, we would see some sort of behavior like this through time, and so on. This is called a flow diagram, and it's pretty useful for certain applications, but for us, maybe it's not so useful because we're interested in making some judgments about the behavior of the system without actually plotting every single one, right? Every single solution. So instead, what we might want to do is construct some depiction of maybe how x depends on y, and show the trajectories in this phase plane of x and y together, right? If we know that everything decays towards 0, we know that no matter what your starting point on this phase plane, you're going to be going towards 0. So you'll have a bunch of trajectories there. There are probably some details about where they end up, how quickly they go to 0, etc. We don't necessarily care about that just yet. But we plot a whole bunch of these trajectories, and we say, so this is how x depends on y. No matter what, x and y are both going to 0 because they have some sort of exponential decay, right? And that's perfectly fine. However, what we have inadvertently done just then, almost by accident really, is we've taken in our heads the following sort of behavior. So this system that I've just defined with exponential decay is actually not this. Instead, it would need to have some additional parameters that guarantee this decay, because the solution for this equation that we have right now suggests that this system grows infinitely. So we get some behavior like that. So when we need to consider decay, what we actually do is we say there's some additional parameter set, perhaps we'll call it A, which acts on our state vector, which again is composed of x and y simultaneously. And this is what our temporal evolution of this state vector depends on, okay? This parameter set that we've introduced to our equation, A, is exactly a linear transformation on the trajectories of some original equation, right? If we had graphed the trajectories of this x equals x, y equals y system, that would be our original, so to speak. And we introduce some linear mapping to something else, some other equation, which has qualitatively different behaviors. We know that all linear transformations have an eigenvector. And so we may be interested now in determining what that is, right? What that might be. Why would we be interested in determining that? Because this transformation mixes x and y together. And we would prefer them to be independent so that we can consider how x behaves, and then we can consider how y behaves. And we don't have to worry about them together. We would consider them to be linearly independent, so to speak. Now, the eigenvectors of this mixing A is exactly isomorphic to the eigenvectors of a linear mapping A. What it gives us is the trajectories of x, in this case, your vector x. So it gives us the trajectories of x and y that are linearly independent of each other, because these eigenvectors are saying under this linear mapping A, they scale by something, but they don't really move. So we're looking for some independence in x and y, such that we may sort of pull them apart and consider them separately. Eigenvectors are the axes along which a linear transformation simply stretches or compresses. And it gives you the factors by which this compression occurs from an eigenvalue. Now, again, once we've done this mixing through A, using these parameters that correspond to some x and some y, we want to decouple the system, so we're dealing with two independent functions, x and y, not the system as a whole, right? By finding the eigenvectors of A, we determine exactly that. What are the sets of trajectories along which x and y can be considered separately? That's why we care about the eigenvector in this case. And that's how the eigenvector relates to the phase plane. It's the direction along which x and y will travel in such a way that we may solve for x and y independently, and we may consider and graph them independently. The eigenvalue that we get from A is how much this trajectory is scaled by, or in other words, how fast it's moving. And we'll get to that in the next video, maybe when I actually work through one of these. So again, solving the system directly would be complicated because we have some complex set of parameters. This might be something really strange, like, for example, say x dot equals some parameter k x plus by, and y dot equals cx plus dy. I've tried to avoid reusing a in this case. This is a system that would be a real pain to solve on our own. Solving the system directly would be complicated. But what we can do now is decouple the system by taking the matrix A and saying, well, x and y is one matrix equals A times xy is another matrix. And I've forgotten my temporal derivatives on this side. If we find the eigenvectors along which A leaves x and y unshifted almost, if we find the vectors along which x and y remain linearly independent from one another, meaning this linear transformation does not act on x and y stay separate, then what we can do is we can actually try and solve this problem using something separate. We can say maybe we sub in k and b and c and d, and we say we do some switching of variables, we get some other expression, and we take the eigenvectors of this, we put it into some solution, and it allows us to deal with things independently. I think this will become a bit more clear in the next video, where I actually puzzle one of these out. I actually solve one of these using these principles. So that's essentially what we're looking at. Are there any vectors which do not change their direction under a transformation A? And in this case, these vectors are trajectories of the evolution of x and y. So we're looking at, where does A give us some expected behavior for x and y, rather than changing it radically? I think this is hopefully a clear explanation of where the eigenvector is coming from and why we bother with it. If you have any questions upon seeing this video, please reach out to me by email or on Neurostars, and I will be happy to clarify things or go over things again. So please think about the content, think about what's been gone over in this video, and Make sure you understand. Any questions, let me know. I'll see you in the second video if you're interested. Take care.